Okay, this is the second page of the Performance Final Study Guide. And now we're looking at energy. Okay, so we did that unit right before the Thanksgiving break. So we're going to do some energy bar charts for a few different scenarios, and that's like what we talked about mainly with the roller coaster, where we're going to be looking at some different points here. And the total energy is already filled in. Remember that due to conservation of energy, this total doesn't change. So you can see it's the same here, here, and here. So what we want to look at for each of these is what energy does the skateboarder have in terms of potential and kinetic, or what combination, okay? Remember that potential energy is our energy due to like our height or our position. We talk about gravitational potential energy. So our equation for that is mass times g times h, where h is our height. And then kinetic energy is our energy of motion. You got to be moving in order to have kinetic energy. So that equation is 1/2 mv squared. And then remember that our total energy, or what we also call mechanical energy, is our kinetic plus potential. Okay. Okay, so the skater's at rest at the top of the track, right? So if she's at rest, that means there's no velocity, no kinetic energy at this point. So all of her energy is potential. All of it is that gravitational potential energy due to her position. So our bar chart's going to look like this. All my energy is potential. And my total equals my total because energy is conserved. This total here is always going to stay the same. Now she's at the bottom of the track and moving quickly. So she has no height here. This would be, H would be 0. That makes potential energy 0. Okay. And she's moving. So all of her energy is now kinetic. So instead of this type of graph, this one we're going to have all of our energy in the kinetic. So I'm just going to draw kind of a highlighted rectangle here. Okay. Okay, and then the last one, she's halfway down the track. Okay, so at this point, she's got some height. She's 3 meters off the ground, but she's also moving. Okay, she's halfway down. And so her energy is basically going to be half of it is going to be potential, half of it is going to be kinetic. So I think this is about, see, this is 1, 2, 3, 4, 5, 6, 7 squares. So about 3.5 squares roughly for each type of energy. So half of her energy is going to be potential, and half of her energy is going to be kinetic. Because she's still got height, so she's still got some gravitational potential energy, but she's also moving, so she's got some kinetic energy. Okay. All right. How much potential energy does she have when she's at rest at the top of the ramp? So here we can calculate potential energy is mass times g times h. She's a 60 kilogram skater. We're going to use 10 for g, again, just to round and make it simpler. And then it's a 6 meter high ramp, so that's 6. So mass times g times h, 60 times 10 times 6. And that's going to give us 3,600. And remember, energy is measured in joules, or capital J. How much total energy does she have when she's at rest? Remember, our energy is conserved. Our total energy is conserved. So if all her energy at the top of the ramp here is potential, then that means her total energy is going to be the same total. It's also going to be 3,600 joules because that's all of her energy at that point. is in the potential energy bucket. Okay. How much kinetic energy does she have after she rolls down the ramp and now she's moving fast? Okay, so here we said earlier when we did our bar graphs that for this situation, all of her energy is kinetic. So again, my total here is going to be that same 3,600. Okay, so think about it from this perspective. Your total energy equals potential plus kinetic. So when she's at the top here, all of our energy is potential, no kinetic because she's at rest. And then likewise at the bottom, again, total energy equals potential plus kinetic. At the bottom, our potential 0 because we've got no height. All of our energy's got to be kinetic. So those just all go back to conservation of energy that we talked about when we did our energy unit. Okay, final question. She's traveling at 10.9 meters per second when she reaches the bottom of the hill. And so, how much momentum does she have? Remember, momentum is mass in motion. The way we calculate momentum is mass times velocity. Remember, P is our symbol for momentum. So, we're just going to take her mass of 60 kilograms and her velocity, which is given to us 10.9. Multiply those together, and that gives me 654, and that's kilograms times meters per second because I'm multiplying mass times velocity. Okay, so that is that's the whole study guide. Not too bad. Just make sure you understand all that, and you should be in good shape for the performance final.